Hi, everybody. Good to see you today. Thanks for being here. We are headed into section 1.3 and 1.4 today. We will be transforming functions and then we will be looking at inverse functions. So, um, our first things first, let's take a dynamic view of what it looks like to shift, reflect, and stretch functions. What you're expecting to see here, we're going to go into GeoGebra real soon. Um, But, if on normal function, just f of x, maybe we call this a parent function. Cool. If we call f of x the parent function, I want to look at transformations on this function when we multiply and add and subtract different things. So, uh, first we'll have a factor a outside that'll be multiplicative. Um, then we can do some multiplication and addition on the inside. So x is still our variable. Actually, hold up. I think I'll do minus h here for reasons that you will see soon. And then plus k. What I would say is that this feels kind of like the function rewritten with some extra parameters in it that we're going to be able to switch around. And this feels kind of like a vertex form. If you're familiar with the vertex form of the parabola, um, we can have different values in these spots, and all of them are going to influence things in a little bit of a different way. Um, let's go ahead and open up GeoGebra, and we'll pay special attention to how this A out in the front um, changes things. So here are two graphs, and picture both of these as parent functions. Um, the green one and the blue one will move, but the orange and red are the parent functions. We've got a sine function that's nice, and then we've got this green weird piecewise function that is part line, part parabola, and then part rational function. The idea with that green one is that it's asymmetric, and hopefully you will be able to see things more clearly because it's asymmetric. But I also wanted to include a sine wave too, so that you could see that. All right, so we're focusing in on A. This is just a multiplicative factor that we're putting out in front of the function. And maybe not too surprisingly, when we include this, it is a vertical stretch because that multiplicative factor is directly affecting the y value, the output of this function. Notice that when a, this value is positive, it's a vertical stretch, and the bigger that a gets, the more stretchy it is. As we go down to zero, I mean, if we left it at zero, yeah, oh, that was so close. Left it at zero, then we would have a completely constant function, which would be boring. But as we go into negatives, notice that we've got a vertical reflection or a reflection around the x-axis. So that is something else cool that that one does. Get me back to 1. Great. Okay, so that's A. Maybe we go back. Well, we'll summarize it at the end. Um, let's stay in GeoGebra for a while. A is great, multiply. B is multiplying on the inside of the function. Um, and so let's take a look at what B does. There, B is getting bigger. And what's strange is that bigger values of B feel like a constriction horizontally of the function. And when B is smaller, it gets closer to zero, it feels like you're being horizontally stretched. Um, and so, especially when you're thinking about this as like a sine wave, B is in the place of what we would call the frequency of the sine wave, or how many of these sine waves would fit into a period of 2 pi. When this is 1, yeah, there we go. When this is 1, uh, over 2 pi, sine fits into it once, but if we were to multiply this and go up to 5, that means there are 5 sine waves that fit into the same um, space. So 5 repetitions. So this B is like a horizontal stretch squish, kind of in a way that you wouldn't expect, but yes, the frequency is inversely proportional to kind of this squish factor. All right, so B is horizontal stretch and squish. um, and when you go negative, it is a reflection around the y-axis. I guess I didn't make a big deal about that, but yep, reflection around the y-axis. Okay. Um, H is on the inside of the function, and I put a minus H here. That's because when we go kind of positive values of H, it induces a rightward shift. It's kind of like, right now H is 2.7, and when we subtract 2.7 off, it's like 2.7 is the new zero. So, 2.7 out here is acting like the origin used to. So, subtracting 5 off puts you all the way out here. Adding 5 on, I know that that's now subtracting a negative, but yeah, adding makes you go, or sorry, yeah. Negative numbers for H make you go left now, and positive numbers for H make you go right. If that negative sign isn't there, then that's going to be flip-flopped. But H induces a horizontal translation. Okay. And then finally, we've got K. K is just hanging on the outside. K is going to affect the Y value, and it's just going to directly affect the Y value by shifting things up and down. And K works as you would expect. Add K, you go up. Subtract stuff, you go down. That kind of good stuff. All right. So, cool. If we go back to OneNote now, this one, great. This one was related to vertical shift, or sorry, vertical stretch. And can do reflections, a vertical reflection. When negative. Cool. Um, this one was horizontal stretch. You know, think of it as related to frequency, especially when you're dealing with trigonometric functions. Um, H is a horizontal translation. Uh, K is a vertical translation. If you like transformations here, you will love transformations when we get to linear algebra. If you ever take modern geometry, the transformations in that class are super cool. Um, but anyways, these are ways that we can take a parent function and change them, but knowing how each of these numbers affects the parent function allows us to more accurately picture things once we know the general shape of the parent function. So this just opens the world as to what kinds of functions you can visualize. Next part, composing and decomposing functions. Function composition is like stuffing one function inside of the other. In this notation, the f of g of x is how we would read it. And generally, we are going to utilize this notation on the right. The notation with the dot is not wrong. It's fine. But normally, we're going to use this because we can see that g is on the inside of x. And the idea here is that when we shove one function inside of the other, now the outputs of G become the inputs of F when we've rearranged it this way. So if we were going to look at the set diagram down below, this is our, first domain. These are our inputs down at the bottom. Those are the X values that we're throwing in. G acts on those X values in some way and outputs something called G of X. This is the range of G, but the range of G becomes the domain of F, and F maps all of those G of X values into a new spot. So, I mean, this is, the middle one's a range and a domain, and then the last one is just the range of a range kind of a thing. You know, this function composition is a super cool operation that is going to allow us to build a lot more complicated functions. And if we see a complicated function, dissect it, and so that we can understand how it's going to behave. So composition is super important. Let's go ahead and take a look at example number 9 here. We've got f of g of 6, and that's the first one we're going to do. So let's just pay attention to that. F is x squared, g is x minus 3. I guess probably as a first step, I would go ahead and write this in a notation that I'm comfortable with, that really shows me that I'm going to put in 6 first, then I'm going to apply g, and then I'm going to apply f. It's like peeling layers of an onion. So yeah, if I do g of 6, that would mean that I'm putting 6 into g of x. And so 6 is going in the place of x. We've got f of 6 minus 3, which would be f of 3. And then f of 3 would look like 3 squared or 9. So not too bad there. The next one is f of g of x. Here we're going to look at it as a function. And that shouldn't be too bad either. Let's go ahead and write it and step by step it real quick. G of x is x minus 3. And then here's the tricky part. X minus 3 is now the input for f. And so x minus 3 belongs on the inside, and then we square on the outside. It's not here right. I guess it's here, not here right now. We could do g of f of x. If you want to pause and do that right now, you totally could. But it looks like that's coming up in the next example anyway, so maybe we could just do that. We definitely want to look at it both ways. Actually, hold up here. I'll leave it like this for a second. If you would like to pause and take it just a second or two to try to make both of these functions on your own, and then, when I start going, you can check with me. Okay, so try that, see if you can write it, and that'll be good. Okay, here we go. Let's scroll down, and f of g of x will look like this. And let's throw in g. G is the square root of x. And then as we apply that, we throw the square root of x underneath the squared, and this should just become x minus 4. Cool. On the right over here, we're doing it in the opposite order. So f is on the inside now. And then, yeah, I'll put f there first. And now we apply the square root to everything. And those are different functions. Let's go ahead and take a look at the GeoGebra thing real quick. Opening file failed. Great. Um, I'm gonna pause real quick. All right, we're back. I don't know why that link wasn't working, but we've got it now. Okay, here are the original f of x and g of x that we started off with. One's just a parabola, one's a square root function. Um, and then here we can look at, actually, wanted to make this a little bit bigger for you all so that you could see that better. Didn't want to mess this up. Boom. Um, So this is what it looks like when you have basically just x minus 4. Do know that since we took the square root of x, this does have a restricted domain. I should go back and I'll try to point that out in the notes. Um, and here's the other function. They're somewhat similar there. They both look kind of liney, but um, yeah, definitely different functions when they are composed in different ways. Um, yeah, I hadn't made a big deal about domains yet, but that's actually something that should be considered, I suppose. Um, for this first function, g of x, let's use purple. For g of x, the implied domain, since we're using the square root of x here, is only positive numbers. X needs to be greater than or equal to 0. For f of x, the implied domain could be anything. That's a polynomial. No big deal there. So as we go through things, x should only be greater than or equal to 0 the farther that we go down on a, and that's why we saw that x only starting at 0 when we were looking at this one. And we get a different domain consideration once we plug in x squared minus 4 into g over here. So that square root consideration comes in when we apply this. And in that case, we want x squared minus 4 to be greater than or equal to 0, which gives us x squared greater than or equal to 4. And this actually gives us the opportunity to break this into two cases. One of the cases, when we're working with positive numbers in for x, that would just mean that x is greater than or equal to 2. 2 squared is equal to 4. When we're throwing in negative numbers in for x, we want numbers that are smaller than -2. And I started writing something, but that's backwards. We want x's that are smaller than -2. And so this is kind of like um, it's an or conjunction between two inequalities. And if we wanted to be fancy and write this in interval notation, because I think it's in the homework, um, we would start off with the one on the right, because that's actually the one that's smallest. So less than -2 means that we go from -infinity to -2, like this. We throw a big old U in the middle for union, and then we go 2 and infinity, open parentheses on the infinities because we can't put infinity in a box. We can't find the end of it. And then hard brackets on the 2 and -2 because we do want to include those in the solution. So that's why we saw a gap in the middle of this one and just going on from x equals 0 on this one. Okay, cool. Great. I didn't even read that part. I'm glad we talked about the domains. Next one. Example 11. Decompose this function into a composition of 2 functions and 3 functions. Cool. You could take a minute to, try that. I think I'm going to try to break it down into as many functions as I see and, peel the onion away, so to speak. As I look at f, huh, I can see that it is a composition of, well, there will be a square function, so that's 1. There will be a -3. There's an absolute value, and there's a +2. So I'm going to contend that, um, yeah, f of x is the composition of 4 functions. Gosh, I know that this notation is kind of awful. Um, that one matches that, that matches there, that matches there. I think that's good. Okay, let's go through and name these functions. F1, this is on the very most inside of the function. It's the thing that we're putting in first in the center of the composition. That would be the squared. The exponent is the closest thing to our variable x. So I'm going to write x squared for that first one. F2, the next closest thing to that x squared is the -3. So here I'm going to write x minus 3. We don't need to write the x squared here because we've already taken care of it in that first function. F3 will be the absolute value of x, and for a similar reason, we're just going to leave it as absolute value of x. And then F4 would be the +2 on the x plus 2 on the end. So that, as we build this up, we would start off with x, and x gets transformed into x squared by f1. And then x squared gets transformed into x squared minus 3 using f2. And then f3 gets applied and transforms things into the absolute value of x squared minus 3. And then f4 gets applied, and we get the absolute value of x squared minus 3 plus 2. And so, that shows you how it's kind of built up. And I know that I didn't follow the directions on this one. If you wanted to make sure that it was just a composition of 2 functions or 3 functions, you could, you know, combine any 2 of these, together and make a more complicated function. You could say that f1 was x squared minus 3, and then f2 was the absolute value of x plus 2. You could just, combine them together. But I thought breaking it down like this into 4 things was kind of fun. Let's go ahead and take a look at this GeoGebra thing, because why not? Hopefully this one works. Yes. All right, so we've got all of those little functions that I just talked about, and I guess this is P, H, G, and F at this point, but that makes this function totally. And I think I made this thing so that it would build it up along the way using if statements. Wow, I am a big old nerd for, making that happen. But really, that's just applying things, in the inside to outside order. X squared first, minus 3, absolute value, plus 2. So that's what gets us this function in the end. Cool. I think that that's it for 1.3, and we can head into 1.4 on inverse functions. All right, so inverse functions, why are they important? Oftentimes we want to undo, transformations or functions. The idea with an inverse function is that if we compose an inverse function with an original function, we should get back to x. So if we drew like a set diagram it would kind of look like whap and whap. Okay. Here's domain with a bunch of x values in it. Here's a range, and I guess this will be the domain will be of f, and the range will be of f over here. So f will be a function that takes values as inputs in this domain and outputs values over in this range. Um, Whereas, an inverse function will do the inverse thing. It's going to take things from the range of f and bring them into the domain of f. We denote it as f inverse like that with a little -1 as an exponent. I know that it's strange notation because sometimes a -1 exponent, you could be tempted to say that f to the -1 would be 1 over f because we're used to -1 being a reciprocal. Not the same. Not the same. What this does is this, utilizes the range of f as the domain of f inverse. And uh, over here, we've got the range of f inverse being the domain of f. So they completely flip-flop. Written out in function notation, that would look like either way you write it, whether you put f inside of f inverse, that should work out to just be whatever the original input that you put in. So you get an x out because you put an x in originally, or even this way too. When you throw an x into f inverse and then you apply f afterward, you should get back to what you originally put in. And so, yeah, these are going to be important in general. They definitely, we're going to look at logarithms and inverse trigonometric functions as examples of these soon. So those are both very important classes of functions. I guess one more thing. Unless I have it. Oh, yeah, it's down here. We'll show that down there. Anyways, this is showing an inverse of a relation, which is just a little bit more general than a function. Relations are allowed to fail the vertical line test. In this class, we're not going to be too interested in relations. We are going to be interested in the functions, though. So if we go down here and we start looking at these parabolas, I want you to notice a few things. First thing is, there is a nice line of symmetry across the line y equals x. When we're looking at when we use the line y equals x there, it's like a mirror image reflection across of that whenever we have a function and its inverse. Super cool. Second, notice that this has to be a relation because we don't have functions both times. The blue one is a function with respect to x. That never fails the vertical line test. But the red one definitely would fail the vertical line test. And so what this highlights is the importance of restricting the domain sometimes so that we have a one-to-one and onto function. One-to-one and onto functions have an inverse function. And what that would look like in this case is if we restricted the domain of R to just be positive numbers. So I guess, what that would look like is erasing this part and just having the front part of x. What that would do is also erase this part on the red one, and then we would have two functions that both pass a vertical line test when you look at them individually. And yeah, you can tell that you are going to pass the vertical line test both times is if you go back and you look at how things used to be, we can tell that R won't have an inverse function because it fails a horizontal line test. We can throw a horizontal line there, and then there are 2 points where that horizontal line intersects R, and that means the vertical line test will fail for the potential inverse. So to tell that a function is one-to-one and onto, the go-to would be, if you have a graph of it, you can make sure that it passes both the vertical line test and the horizontal line test at the same exact time. If you don't have a graph, really the property that you're looking for is that every element in the domain gets mapped to one and only one element in the range. So one element, or yeah, I guess any element here. Let's say any. That's better. Come on, eraser. There you go. Any element in domain gets mapped to one unique element in the range. So that way, that process is reversible. If you're starting off in the domain, you go to the range will just do the exact opposite and bring you back to the original domain. Sorry, yeah, that's what the inverse function will do. Cool. This notation definitely doesn't stand for 1 divided by f. Totally there. We already talked about that. Okay, the question is, when does a function have an inverse? I guess I just started talking about this one-to-one functions, utilizing a horizontal line test as well. Let's go ahead and take a look at these little diagrams that I posted so that we can get another example. So for the first one, our function is x plus 1. F is x plus 1. So what that does is it takes a number 3 and maps it to 4. It takes -2 and maps it to -1. It takes 7 and maps it to 8. Cool. The inverse function happens to be the blue function there, x minus 1. This is totally invertible. They're both just lines, but are both symmetric around the line y equals x. Yeah, but we can totally subtract 1 and go back to 3, or back to -2, or back to 7. That process is totally invertible, reversible, no problem. But when we go and we look at that second example where we had parabolas, let's look at the mapping. From the domain, 2 squared would get mapped to 4. 5 would get mapped to 25, and then -2, gets mapped to 4 as well. X squared is a perfectly fine function, but the problem is when you try to define the inverse. So if we try to follow these back, 25 is not a problem. 25 just gets mapped back to 5. And if we were to follow this as an inverse function, 4 would get mapped back to 2, but it would not get mapped back to -2. In order to accomplish that part, we would need to utilize a function, the negative square root of x. And so, that doesn't actually exist right now. And so this potential inverse function is not inverse on this, domain. But if we limited ourselves to only non-negative numbers in the domain, then we would have a perfectly invertible function. So that's what we did, when we erased this stuff up here. When we take out the negative numbers, we get nice invertible function. And so if we took out the negative numbers here, we would be invertible and we'd be fine. Okay, vertical line test, horizontal line test, we talked about that. That's cool. Um, Example number 2, determine if the following functions have inverse functions. Okay, cool. First one is the absolute value of x. The problem here is that we fail the horizontal line test, and so, there are two elements in the domain that both get mapped to the same thing in the range. +3 gets mapped to 3, and -3 gets mapped to 3. And so if you were going to try to invert this, um, you'd have a problem that, the inverse would not be a function anymore. It would have two outputs for every input, which is bad. Um, let's look at B then. B is this cubic function, or yeah, we've got g of x here. It's a cubic function. Um, Notice that if you look at the graph, this thing would pass a horizontal line test everywhere, in the range. It would pass a vertical line test everywhere where we're looking in the domain. And this one's actually going to be really nice. Um, the property of being one-to-one can sometimes, if you're like doing more of a mathematical proof type of thing, can be stated this way, such that if you have two different things in the domain, yeah, two different things in the domain, and you put that through the function, it should imply that they are two different outputs in the range. And so what this really signifies is that things are unique. Um, if you have different things in the input leading to definitely different things in the output, it means that you have a unique relationship where you're going to be able to go forwards and backwards without a problem. The next thing that I want to do is actually find the inverse of G. So let's find G inverse. Um, the first step would be exchanging the roles of X and Y. Um, yeah, I mean, I didn't make a super big deal about this earlier. Let's go ahead, let's drop here. Um, Remember that line y equals x is like our line of symmetry. Whenever we have a point on a function f, let's call it ab, the function that will, or sorry, the corresponding point on f inverse will be BA. Literally, you just flip-flop the x and y values. So that's what we're going to do when we're finding this g of x. And, let's see what happens when we go in this process. So I know that this part feels wrong, but what we're going to do is, take g. Let's say we've got y equals x plus 2 cubed. And so this is, corresponding to g. But if we want to find G inverse, we flip flop and we exchange the roles of X and Y, and then we solve for Y. So in this case, it would be good to take a cube root on both sides, and we'd be left with Y plus 2, and then we'll be able to subtract 2 from both sides. And this is now our inverse function. And, maybe we could leave it as, an exercise that you guys could do. But if you did either one of these compositions, if you put in G inverse into G, or you did G into G inverse, both of those should turn out to just give you X in the end. So if you wanted to try composing those and making sure that you get X out in the end, that'd be a good thing to do. Cool. I think we're good there. All right, scooch over a little bit, keep going down. I guess now we're officially on topic two, where we find inverse functions. This is the same, thing. This lists out what I've been writing several times already. That's our goal in finding an inverse function, is something that behaves like when you put an input in, you get the same thing as an output. Cool. Here are some steps for finding an inverse function. If, this was unclear, possibly looking at these steps for a while and, you know, try to make sure you follow them. It does the same thing as what we just did. This is just exchanging the roles of x and y in the equation and then solving the new equation for y. Find the inverse of each of these following functions. We just did that one. I mean, basically, it's pretty much the same. If you guys want to take some time and work on that together, totally fine. Otherwise, maybe I'll just do B for now. If you want to do A too, it's fine. But I want to make sure that I'm not keeping you too long. Okay. So that's what G looks like if we were, I guess G would correspond to y equals x minus 3 over 2x plus 1. And if we went to G inverse, we would exchange the roles of x and y. X equals y minus 3 over 2y plus 1. And then we try to solve for y. I think I would multiply both sides by 2y plus 1. Let's go ahead and use the distributive property there. 2xy plus 2x equals y minus 3. Let's get all the y's on the same side. So let's go 2x plus 3 and y minus 2xy. Then we use the distributive property again to go 2x plus 3. We pull the y out. That's 1 minus 2x. And then if we divide both sides by 1 minus 2x, I think we'll be in business. There we have y, and that's G inverse of x. Let's go ahead and take a look at the GeoGebra thing. Yeah, I guess I can, if you need more time to look at that, feel free to pause. It's totally cool. Whoa, so many inverse functions. All right, so bop, bop. Okay, this was the first set of inverse functions that I didn't bother doing right now. But notice how we have a nice one-to-one function, so the entire thing is invertible, and how they are mirror images over the line y equals x. Totally cool. And then this was the second set of examples. This one's maybe not as easy to see, but yeah, here the blue and the red are acting as inverse functions, and they are mirror images across that line y equals x. And, if we were to compose them, I'm going to go ahead and do it either way. Blep. What? Oh, I made mistake. Well, that's actually, good to realize. What? G and P are, I totally typed that in wrong. All right, rewind this back. G looks fine. P as a candidate for an inverse is garbage. This should be bop, 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 2x plus 3. Whoops. And the bottom should be 1 minus 2x all over the place. 1, 2x. Ew. That still doesn't look good. Um, because when we compose them, we should just get a straight line, y equals x. And this thing that's curvy. What's going on? Pause. Be right back. Okay. Unpause. Um, I found my mistake. I had a 2 up here. It didn't belong there. Let me go back to um, the work that I did and show you where I messed up. Apparently, x times 1 is not 2x. It's just a regular old x. So that belongs like that. That belongs like that. And all this too. Hopefully you guys found it before I did. I bet somebody did. Um, anyways, when we get rid of that 2, and then we just have an x, things should work out nicely. And indeed they do. When we look at the inverse, composed with the original function both ways, both of these end up just being the line y equals x, which is what we want as the result of composing inverse functions. So we're okay now. We continue. Cool. Oh, I actually just copied this from the book. I just want to do it all. Uh, but this is what it actually looks like to compose those things and see that it works out to just x in the end. So here we're throwing g into the inverse function and reducing that by, multiplying and all that good stuff. Reducing things down does in fact get you to x. Yeah. So that's cool. And then a similar calculation would go the other way. All right. On to the second to last topic. Yes, topic 3 is logarithms as inverse functions. Okay, so if we looked at this first equation, it would not be too bad to just do this by inspection and think about what exponent would we need to put on 2 to get 8. The answer, x equals 3. No problem. Over on the right, what exponent do we need to put on 2 to make it equal to 9? Not so easy. It's going to be some irrational number. What we can do, though, is utilize the fact that exponents are the inverse to logarithmic functions. And so as we exchange the roles of x and y before, we're going to utilize this relationship to go back and forth in between exponential and logarithmic expressions of the same thing. So if we go back up to 2x equals 9, what we could do is rearrange this into the logarithm form. So the base of the exponent over there is 2. That means it belongs as the base of the logarithm over here. And now we are kind of exchanging the roles of x and y, or in this case, x and 9. So we can throw in 9 right there, and that equals x over here. And so the value for x, the thing that would solve that original equation, is log base 2 of 9, which is its own just irrational number. It would be slightly larger than 3. And I guess, we could put that into a calculator if we were really curious about this. Actually, we should be curious about it. When you go into GeoGebra, it looks like there is a special log base 2 function, but if you didn't have that, you could use this one, which asks you to put in the base first. So the base was 2, and 9 was the thing that we were putting into the argument of the log. And yes, it's a little bit bigger than 3. It's about 3.17. Cool. So that means if we took 2 and we raised it to the 3.17 power, we would get really, really close to 9. It's a big, long, never repeating, never terminating irrational number. But we're utilizing this relationship between inverse functions when we utilize logarithms. Super cool. Yeah, like logarithmic function is defined to be the inverse of the exponential function. So super cool. Um, Here we could look at a couple of cases. This is what exponential decay would look like whenever you have an exponent in between 0 and 1. That exponential function is going to decay over time and get smaller. Um, the corresponding logarithmic function would be the mirror inverse flipped over the line y equals x. Over here, this is probably more familiar. We've got exponential growth, and that's because the base is bigger than 1. And here the logarithm is there. I guess one of the things to point out here is that, yeah, these are inverse functions, and the range of the exponential function, notice that that's always positive numbers, and notice that the domain of the logarithms is also always positive numbers. So don't try putting a negative number into a log because that would be outside of the domain. Log base 10 is called the common logarithm. Log base e is called the natural logarithm, and we use ln of x a bunch in this course. The base e is super special to calculus. E to the x is the only function whose derivative is itself. It means that the rate of change of e to the x is the same of the value at any given x of, e to the x. It grows exactly proportionally to how big it is at the current time. Let me go see and click this, what happens. Oh yeah. All right, so we're looking at e to the x, and I'm trying to show you what I'm talking about here. So the y value along the curve, the y value of this point, will equal the slope of what's called a tangent line here. So the rate of change of this function is the exact same as the y value that you're at. So, if we went e to the 0, come on, there we go. Um, Notice that, this function has a y value of 0, and also at that spot, it has a slope of 1. So y value of 1, slope of 1 matches. E to the x, super cool. If we go out here, we've got a y value of 2.46. We've got a slope of 2.46. The slope of this thing just matches the y value at every point. Super cool function for calculus. We're definitely going to talk more about that as we learn about derivatives and integrals. Okay, last big section here, and it's actually not too crazy. Looking at inverse trigonometric functions. Here we've got, oh great, I'm getting a call. Okay, sorry about that. We're here on inverse trigonometric functions as our last example of inverse things. A normal trig function would take in an angle as an input and output a ratio of side lengths on a right triangle. The inverse trig functions do the opposite thing. They take a ratio in and output an angle. So, here we're looking at arcsine. There are some special considerations here when we look at arcsine in terms of the domain that we should use. So, our goal for choosing a domain for sine would be looking at this graph and trying to pick a portion of sine that goes all the way from its minimum y value all the way up to its maximum y value. And since sine is an odd function, it's centered about the origin, And starting off from negative pi halves and going up to pi halves in the domain means that we go from -1 to +1 in the range. And we have a nice one-to-one section of sine to use. Over here is arcsine, where we've got 1 to -1 as those input ratios, and then output angle measures. And so, yeah, this is the best spot to get the entire range of sine covered. If we go down, here is cosine um, and arc cosine. Notice that for a cosine graph, since it's an even function and symmetric about the the y-axis, we start off here up at the top of the function when x is equal to 0, and we can go through all of the y values of the function as we go till pi in the x value. So that's what allows us to cover all of the domain and range that we're interested in, and doing the inverse of that allows us to graph arc cosine this way. So there's just a little bit different domain chosen for cosine and sine when we're thinking about inverting them, but it's just because of the symmetry of these functions, and we want to capture all of the y values here so they show up as x values here. Capture all the y values here so that they show up as x values here. Super cool. Over here is tangent and arctangent. Arctangent's cool because, you can put anything into arctangent and it'll output a value in between negative pi halves and pi halves. So unlike the other ones that have a very, restricted domain there and there, infinite domain there, cool. It's because we got infinite range here. All right, and just to end things off, here's a little table about, um, arcsine and cosine. One thing that I didn't specifically say is that, these notations are equivalent. Writing arcsine is completely fine. Writing the sine with the inverse thing there means exactly the same thing. I think this one is the one that will show up in Hawks when you choose it using the calculator thing. So, thanks for listening. I hope you have a nice weekend. Happy Calculus Friday. And I guess we're gonna see you on Tuesday. Um, so talk to you later. See ya. And boom.